كان تخرج قبل سنه كان هو موجود يعني ماستر.
We're gonna start guys.
بس ما سوى رسالة صح؟
ما ادري والله.
لأن لو كان في رسالة كنت بعرف أكيد.
ما اعرف يعني. كان موجود هنا. كنت اقول لك كيف انا كنت اقول لك ايه.
طالب بلال ايش
خايفة اجيب مطفش اسئلة.
No, bring him. He's here. ايوه جيبيه.
انا احسن موضوع.
كويس والله. يعني نطلع منه ولا ما انا بعد انا حاجه ثانيه كثير يعني طويل الصيف. كنت ادور انترنشيب هناك وجاء البرتقال يسوي لنا هناك جاي انترنشيب في الموضوع.
لا كاوست فرصة حلوة مرة. حتى بإذن الله أنت في المستقبل بعد ما تتخرج ترجع للجامعة بإذن الله إذا حبيت تسوي تعاون أو شيء مع أحد في كاوست.
تكون عندي عارف كذا الدنيا الناس موجودة كويس والله.
يعني حتى لو لسه ما سويت الشيء هذا أنا أنصحك أنك تزور الجروبات الثانية اللابات الثانية الإلكتريكال.
صح.
عشان مستقبلا أنا ما أدري وش المجال اللي أنت بتتخصص فيه في الجامعة، بس إذا حبيت تسوي تعاون حبيت تسوي شيء هنا ترى ممتازين جدا. خصوصا ان كاوست الان والبترول صاروا كلهم تحت وزاره الطاقه. فالمفروض انه يكون في تعاون.
Yeah, we thought this is better.
اللي كنت بعد شيء اسمه من زمان يعني في تعاون.
We can start. يلا. ايوه. No, take it for sure. I'm going to use it. Okay, بسم الله الرحمن الرحيم. Today we have a simple example, but not so simple. We're going to study the dynamics of a simple pendulum. So essentially we need a function of theta of t. So can someone tell me how many coordinates do we have? How many degrees of freedom? I have two. One? Which two? So degrees of freedom is, the motion allowed, like so. So one is the right answer, theta. So the coordinate we have is theta. Reference frames. We really need to establish that because that's really important for the analysis. So we have the inertial reference frame, E1 pointing down, and we have E2 pointing to the right. And we also need another reference frame to make our life easy. Any suggestion? If the motion is in a circle, what would make our life easy in terms of coordinate systems? We have spherical, cylindrical. We have polar coordinates, right?
Polar coordinates.
Yes.
ER and theta.
Yes, so you can imagine that ER is along here, and E theta is in the direction of increasing theta. Okay? And we have an implied direction, E3, that is shared both in between the polar coordinate system and the rectangular coordinate system. Yeah? So, what we described is we have an inertial reference frame. We have a 0, E1, E2, E3, and we have the B reference frame. Let's call this B, and let's call this I. So the B is 0, ER, E theta, and E3.
What is this one? Zero? The first zero?
0 is the origin.
Okay.
So in order for us to get a reference frame, we need an origin, and we need a triad of vectors. The definition is that E3, which is the third direction, is always E1 cross E2. That's the definition. So when you cross, right-handed rule, you get E3. So yeah, E1, E2, same direction. Okay. Let's draw the free body diagram. So it's a point mass. What do we have in terms of forces? If you pull this and you let it go, What forces do we have? We have gravity. Yes. So it will be mg in the positive E1 direction. What else do we have?
Tension from the cable.
Yes. How would you write that? Yeah, but like how would you express it in math? We don't know the tension, so you can assume it's not known. Hmm?
T times ER.
Right. But negative ER, right?
All right.
So now we have a good foundation to start. So when you're dealing with dynamics, the best way is to get the position vector, which is R. So you can imagine the position vector that represents the P with respect to O as going from here to here. That's just the position vector. Okay? So what is R in this case? Because that's the start of our derivation. Can someone tell me what's R? If this is the length, R as a vector.
You want it in the Cartesian coordinates?
Um,
Like in
yeah, but if you do it in polar, you have one component, so it's
yeah,
easier.
you have one component.
Yes.
So you want it in I?
In polar. In B. In B. Yes.
So it's R times the, it's like the length?
Yes, so it's the length,
The length times
ER. Right. So, now we need the velocity. So, the inertial velocity is the inertial derivative of the position vector. The inertial derivative, because that's what goes into Newton's second law. Okay? Newton's second law doesn't apply, in non-inertial frame. As you know, F as a vector equals ma, but this has to be in the inertial reference frame. Inertial meaning non-moving. Okay, so let's derive this vector. Or let's take the derivative. What do you guys think would be the derivative? So it's a vector. So we're taking the derivative of a vector.
L is a constant, so it will be not.
Yeah, but we need to use something called.
R is not constant, so it has to be differentiated.
Yes. So we need to use something called the Transport Theorem. The Transport Theorem says we take the body derivative of the vector, okay, plus, because this thing is rotating with reference to the inertial reference frame, so it has an omega. So it has an angular velocity. So we need to do cross RPO. So this is called Transport Theorem. Okay? So, what is the derivative of the R vector in the B frame? Do you think the length of the vector is changing? So yeah.
No.
No, just the direction.
So this is 0. Okay. So now we need to figure out what this is to be able to cross it with this. What do you guys think the value of this? Theta dot. Correct. In what direction?
A theta.
Tangent to the R.
So it's rotating this way.
E3.
So it's E3. So now we have what we need. We do theta dot E3 crossed with, what is our R? Is L,
Yeah.
LER, right? So what do we get here? So these are constants, we can pull them out. Or not constants, sorry. We can pull them out of the cross product. E3 cross ER. What do we get here? E theta. So ER, yes, ER with, yeah, with E3, yes, E theta. So now we have the velocity. Okay. Do you guys know the linear momentum? Anyone knows the linear momentum?
Mass times velocity.
Mass times what?
Velocity.
Right. So the mass of P times the inertial velocity. So, what does this tell you about the linear momentum vector? Where is it?
Same direction as the velocity.
Exactly. So it's in the same direction here. That's P. And it's just scaled by the mass, right?
It's this direction.
Well, it's in the same direction as V.
Yeah, V is
Ah, sorry.
this direction.
That is correct. Right. E theta. Yes. What is the angular momentum, guys? The angular momentum. Hello.
Moment of inertia times the angular velocity.
Moment of inertia times the angular velocity. But you can make use of this to get it simpler.
The linear momentum times the radius.
So it is the RPO crossed with the linear momentum. So in which direction it would be? E3, right? Okay, let's get the, so we have the velocity here. Let's get the linear momentum. It's just m L theta dot E theta, right? Just the velocity times the mass. What is the angular momentum? We know R, right? Crossed with ml theta dot E theta. You can pull the coefficients. It's ER crossed with E theta. What does this give? E3. So now we have the linear momentum. Okay, let's sum the forces on the particle. Let's represent it as a vector. Let's represent this as a vector. So what do we have? You can just say it's mg E1 direction, right? Minus tension times the ER direction, right? They are in different bases, but that's fine. We can still deal with it. So,
You don't want them to be in the same basis? Because well, if you want, you can write it as a function of the time. They are kind of dependent.
yes, we can represent it, but for us to write it, we can write it this way. We can transform later when we do the computations.
Okay.
Yes. So, what is the moment of this force? The moment, as you know, is just the R crossed with the F, right? You guys know? Very simple. So, we have L ER crossed with mg E1 minus F ER.
FER will cancel off.
Yes, so this will cancel, right?
Yeah.
Because it's perfect. Yeah, it's in the same direction, right? So we're left with this. So L mg ER crossed with E1, right? Now we transform. So we know that, let me draw it in here. So if you imagine the reference frames like this, that's E2, that's E1. That's ER, that's E theta. Let's get a relationship between the reference frames. So we have this as theta. Can someone tell me what's E1 in terms of ER and E theta?
Minus cosine theta.
Yeah, I mean, let's get, so we can do cosine, right? So cosine of theta in the positive, and it's minus sine theta of the E theta. Does this make sense to everyone?
You are talking about E1 or E2?
So we want to write E1. We want to get the components of this frame. We want to rotate it, and put it in the E1 and E2 directions. So ER is in the positive,
No.
E2.
Is it E1 or E2? Is it E1 or E2? This
I'm looking for E1
Okay.
because I need E1 there.
The cosine ER, is for E2.
Oh, right.
I think this results for E2. What you write right now.
Right. 1 second.
It should be minus sine theta. ER plus cosine.
Plus cosine, right? So plus cosine E theta, right?
E theta, yes.
Yes. So cosine theta. No, hold on 1 second.
Just draw the extension of ER.
Yeah. So
And then
extension here.
theta is up. Yes.
So theta is here,
Yes.
right? So what do we have? So this is E2. Let's get E1. So E1 is cosine theta ER. I know.
Minus sine theta AR.
Minus sine theta
minus
ER, yes, plus cosine theta
المفروض بوزيتيف ولا
theta.
لانه define ال E1 تحت. لو ديفاين هنا فوق تكون بوزيتيف.
I'm not sure because they're in different directions.
cosine ER. E1 is negative sine ER plus, yeah. Okay. So now we can do the cross product here. So we have a negative sine,
ايوه
sine theta.
Can I interrupt you just
بس انا احسها
Yes.
بوزيتيف ما هي
the
نيجاتيف.
diagram that you have
Sine.
here is different from the one that you have. The theta is between E1 and ER.
Oh, I mixed them up.
Yes, you mix them up.
Yes. I was like, what's going on?
Oh, okay, yeah. It makes sense.
So,
Where you have E2, I think you should have E1 and then ER.
yeah, so this is E theta. This is ER. So yeah, thank you.
Okay, now it makes sense.
Yes. So now we put it in the cross product. Crossed with E theta. So ER crossed with E theta, E3, right? Positive E3, so negative mg sine of theta E3. Okay.
استخدمنا دي روتيشنال ماتريسيز
ايوه عشان كذا اقول لك.
تكون ايش اسمه؟ ما اسال
We know that the rate of change of the angular momentum is equal to the moment. Okay? How can we use that? So we have the angular momentum, right? Let's take a derivative of that. So let's do the inertial derivative of hp of O. What do we get? What's the derivative of this? What's changing here?
theta.
Yes. So we have M L. We have a square here, right? Square theta double dot in the E3 direction. So this is equal to this. You guys see it? Because of this, this is a fundamental of dynamics. So we know that from this we can now equate both sides. So ML squared theta double dot E3, or we can just drop the components because we know that they're all in the E3 direction, and we can say negative LMG sine theta. Right? I like to have the theta alone, so I can just say that theta double dot is negative G over L sine theta. What is this equation in terms of theta?
This equation is what?
In theta, what is it? What kind of equation is it?
Differential equation.
Yeah, it's an ODE. Second order, right? So now we can solve. We can use MATLAB to get the solution. But it's a nonlinear ODE, right? Because we have the sine theta. So, anyone knows how we can use this in MATLAB? What do we need to do? You guys remember that we can get two first order from one second order. So we can say that x1 is equal to theta,
Oh, okay.
x2 is equal to theta dot. Then we can write the system as x1 dot equal to x2. x2 dot is equal to negative g over L sine theta. That's it.
Now what is your model? Is the theta double dot?
This is my linear model, or this is my two first order equations that represent the system. Yes. I think that's it, yeah? Any questions, guys? I guess the most important thing you need to know is the derivative of a vector. You need to apply the transport theorem. So you take the derivative in the body frame, in the frame that it's moving, and then you add the, what is it called? The angular velocity crossed with the position vector. And I would say memorize these. Yeah, that's it. Thank you, guys.
Thank you.
Oh, we can leave it.
This
I can stop it.
other one gets.
You were late, man.